All right, so in section 4.1, we're going to talk about inverse circular functions. We're going to do a little college review that you might recall about inverse functions. That in order to be a one-to-one function, you have to pass both the vertical and horizontal line test. Both of these functions that I have here, f of x equals x cubed and f of x equals x squared, you might recall in college algebra referencing these, they both pass the vertical line test. However, the parabola does not pass the horizontal line test. And here's the issue that we have, is that if you take f of x and you start with the 2, you square it, you go to 4. And then if you take the square root of 4, you come back to 2, which is what's supposed to happen if you're a true inverse one-to-one function. But if I start at -2, I go to 4, and then I ask for the square root of 4, I come back to +2. I'm supposed to come back to -2. You can't have two x coordinates that generate the same y coordinate. In order to be one-to-one, every x corresponds to one and only one y, and every y corresponds to exactly one x. So if we were to find the inverse function of f of x equals x cubed, you take out the f of x, put in a y, switch the x and y, that's the important concept about inverse functions here, solve it for y, and you get y equals the cube root of x. So what happens here, if we graph this, if x is equal to 1, you cube it, you get a 1. Go to the inverse function. You start with the 1. All right, that's the value you just got. You take its inverse, which is the cube root. You come back to 1. We're right back at the same spot. All right, so the same thing. If I went to 2, I cube it, I get an 8. And I start at 8, and I take the cube root, I come back to 2. Where over here with the square root, put in the y for f of x, switch the x and y, and solve by taking the square root, you get a plus or minus. You have two equations, so it's not one-to-one. You do not have a true inverse function based on x squared. Y equals a positive square root of x. That's this graph right here. That matches perfectly for the inverse of the right side of the parabola, but now you got this excess over here. If we say it's the negative square root of x, that's this part graph, that matches the left side, but not the right side. So to turn x squared into a one-to-one function, you restrict its domain. It's no longer the traditional all real numbers. We're going to stop from 0 to infinity. So wherever the vertex is located, to the right, x is greater than or is equal to 0. That's going to give us the positive square root of x as its inverse function. Now, if again, bring back my graph, there it is. Now it's a perfect match. If you flip it over the line y equals x, some people call y equals x the inverse line. So if you flip the original graph over that line, it should match your inverse graph perfectly. So let's take this to our sine function. So if we're going to have an inverse sine function, you simply switch the x and y's around. Now again, let me state this. This right here, x equals sine of y. This is the inverse equation to this equation. Y equals the inverse sine of x. This is the inverse function. There is a difference, and I'll show you that when we get to tangents in terms of the graph. So if we look at our sine curve, again, starting at 0, 0, then at 30 degrees, we're at a half, 90 degrees, we're at 1, and we make all those points, and we graph it all the way, we're going to restrict the domain of our sine of x to -pi/2 to pi/2, because we need it to be continuous, and it has to cover all your y's from -1 all the way up to +1. Everything else on the curve, gone. We don't want it. All right. Now, to graph my inverse function, again, here's the inverse graph right here. Inverse function, not inverse graph, inverse function. Notice here we had before these rectangular grids, which were drawn to scale, approximately 1.57 This is 1, so it should be more of a rectangle. But now your x-axis, which is in radians here, becomes your y-axis. Negative pi over 2 to pi over 2. The y's from negative 1 to 1, they now become the x-axis. And these horizontal rectangles now become vertical rectangular grids. So again, as we pick a point, negative pi over 2, negative 1, now it becomes negative 1, negative pi over 2. Negative pi over 6, negative 1/2, now it becomes negative 1/2, negative pi over 6. 0, 0, 0, 0, pi over 6, 1/2, 1/2 pi over 6. Pi over 2, 1, 1 pi over 2. And there's my inverse sine graph. Now, if we wanted to graph x equals sine of y, then we would have to take this entire sine curve and continue making that sine wave. It would not pass the vertical line test because it's not an inverse function graph, it's an inverse equation graph. There is a difference. All right, so again, we're restricting our domain, whether we have y equals the inverse of x, inverse sine of x, or y equals arc sine of x. They both mean the same. They both stand for x equals sine of y, where we restricted our domain on our original sine graphs to get these new y values. Again, those are the radian measures on the y-axis, no longer the x-axis. All right. Again, you are going to be finding the angle. We did this with the calculator. The calculator was finding the angle, but we did all quadratic or quadrant 1 angles first. So now we have negative angles that are going to show up. All right. So going back to my graph here real quick, I wanted to add one more thing. All right. We are going to need your 30, 60, 90 right triangle, your 45, 45, 90 right triangle. All right, we're going to need these to help find our values. And the other thing that we want to start to build, you want to start to build this on your note sheet. Remember, we used to do all students take calculus. Well, now we're going to do one for inverse trig functions. So as you can see in our picture here, 0 to pi over 2, that's quadrant 1. So inverse sine of a positive value gives you a quadrant 1 angle. And then we went over here to the negatives. This is quadrant 4 going in a negative direction this way. So if you have inverse sine of a negative argument, you come up with a negative angle here in quadrant 4. Okay, again, these are going to be negative angles. So keep that note. We're going to build on that. All right, example time. So let's find these radian measures without our calculator. So we're looking at those 30, 60, 90, 45, 45s. Inverse sine of 1/2. Okay, I know that sine of 30 degrees is 1/2, so 30 degrees as radians, that would be pi over 6. It's going to be positive because you're in quadrant 1. Arc sine of -1, that's the same as saying inverse sine. Well, that was the first point I found when I was switching over from sine to inverse sine. That's at negative pi over 2. Inverse sine of a negative square root of 2, immediately think of a 45-degree angle. That's pi over 4. But again, because it's a negative argument, we're going into quadrant 4 as negative pi over 4. Inverse sine of -1/2. Okay, that's pi over 6, just going in a negative direction. Arc sine or inverse sine of -2. That, wait a minute. We went from -1 to 1. This is not within our range, so therefore this does not exist. Square root of 3 over 2, that's going to be my 60-degree angle. That's pi over 3 in radians, but since it's a negative, we're going into quadrant 4 as a negative pi over 3. All right, cosine, we're going to do the same thing. Looking at our cosine curve, we need to use quadrant 1, but then notice in the quadrant 2, we all of a sudden hit our negative, so we are continuous from quadrant 1 to quadrant 2 on our unit circle. So that's going to be the domain restriction, 0 to pi. So if we want to graph it, now notice -1 to 1 on my y-axis is down here. This is my x-axis on the bottom. It's not here. That's pi over 2. My x domain restriction, 0 to pi, is now on my y-axis, 0 to pi. So my first point, starting up here at 1, 0, 1, is now 1, 0. Then at pi over 3, we'll be at a half, so 1/2 pi over 3. Pi over 2, 0 is now 0 pi over 2. 2 pi over 3, -1/2 is now -1/2 2 pi over 3. And pi comma -1 is now -1 comma pi. That's my inverse cosine function graph. If we just wanted to graph x equals cosine of y, then my cosine curve would keep following that wave pattern in a vertical direction. So again, 0 to pi is going to be my y's on the inverse graph. These are the angles. Okay, well, all right, hold the phone. Let me go get that graph again. 0 to pi, that's quadrant 1. So let's add to our list inverse cosine, positive argument in quadrant 1, but inverse cosine of a negative argument is going to put us in quadrant 2. That's the pi over 2 to pi right here. So for cosine, you will never get a negative angle back. All right, examples. Inverse cosine, -1/2. Okay, that's putting over in quadrant 2. For cosine of 1/2, I believe that's 60 degrees. So we need a 60-degree reference angle in quadrant 2. That puts us at 120, or 2 pi over 3. Arc cosine of radical 3 over 2, that's going to be a 30-degree reference angle, but negative puts us in quadrant 2, 30-degree reference angle, 150 degrees, or 5 pi over 6. Inverse cosine of 0, that's when we are at pi over 2. That's when we're going from 1 all the way down to the 0. That's pi over 2. All right, inverse for tangent. Okay, here's my, now here's where you can see what I was talking about, the difference between an inverse equation and an inverse function. This is y equals tangent of x. This is a function. It's not one-to-one unless once we restrict our domains to our first pair of asymptotes. This is fine. Okay, but if we're just going to go y equals tangent of x, we get the rest of all those iterations. If we go x equals tangent of y, then you get all those extra iterations going vertical here. But once you say y equals inverse tangent of x, then it's just the one in red with the restriction. So here we have the same restriction as sine. Okay, wait a minute. Let's go get my iPad here. Let's put that in. All right, inverse tangent. Positive value in the argument, we will be in quadrant 1, but we got to be just like sine. So inverse tangent of a negative argument puts us in quadrant 4. That's going from 0 to negative pi over 2 in that negative direction. All right, evaluate in degrees without using the calculator. Inverse tangent of -1. Negative angle 1, that's where your square root of 2 over square root of 2 for both sine and cosine are divided, and you get a 1, so that's a -45 degrees. B, arc tangent or inverse tangent of negative square root of 3 over 3. That's the same as negative 1 over square root of 3. And if you think back to that sums and difference identity, we talked about tangent, and I said there's two angles you want to work with when you do sums and differences, obviously 45 degrees. And then there was the question of whether using 30 or 60 degrees. And 30 degrees always gives you 1 over the square root of 3 for that reference angle. So this is 30 degrees. All right, so since it's negative, negative 30 degrees going into quadrant 4. Inverse tangent of a positive square root of 3, square root of 3 over 1. This was the better one to use in those sums and differences. This was, we said, always use a multiple of a 60-degree angle. So that's why we want to use 60 degrees, because you get a better looking fraction. Square root of 3 over 1 is better than 1 over the square root of 3. Example 4. This is where they're going to try to fool us. They're going to do some composite functions. They're going to have a regular trig function and an inverse trig function. And if they happen to match up where the outer function and the inner function, these two are inverses of each other, they're trying to make you think, oh, you can just cancel them and say the answer is 1/2. Well, that's true as long as everything's in quadrant 1, where everything is positive. So here, 1/2, that would give us inverse sine of 1/2 is either 30 degrees or pi over 6. That's my angle. Now you bring the outer function, you say, what's the sine of pi over 6? Okay, that's 1/2. I agree. This one you could cancel both out and say it's a half. Here you can't do that, even though they're both inverses of each other. 135 degrees is starting in quadrant 2, so you have to do each step. It's better to do each step anyhow. So sine of 135 degrees is a 45-degree reference angle in quadrant 2, so that's square root of 2 over 2. Now, the inverse sine of square root of 2 over 2, it's positive. This puts me in quadrant 1 for a 45-degree reference angle. Notice these did not come out to be the same, so that's why we have to do these inner and outer, each one individually. All right, C, tangent of inverse cosine of 0. We just did that. That was pi over 2. And now we're going to look for a tangent of pi over 2. So at pi over 2, we are at, let's see, on the unit circle, we're at 0, 1. So that's sine over cosine. Sine is 1. Cosine would be 0, but that's undefined. So no answer there. Inverse cosine of sine of 5 pi over 3. 5 pi over 3, I believe, is a quadrant 4 angle, and that's, let's see, that would be a pi over 3 reference angle. That's going to be the square root of 3 over 2, but because I'm in quadrant 4 for sine, that's negative. Remember, sine is positive in quadrants 1 and 2, negative in 3 and 4. Now we take the inverse cosine of this negative square root of 3 over 2. For inverse cosine, that puts us over, if you check our chart so far, that puts us in quadrant 2. All right, so that's a 30-degree reference angle, and quadrant 2 would be 150 degrees or 5 pi over 6. E, this is not any special sides to our special right triangles. So now you have to build a triangle. Inverse sine of 1/3 means you build a quadrant 1 right triangle. Always putting the theta in the lower left-hand corner, because that's kind of like, if you will, that's where the origin's at. Opposite 1, hypotenuse 3, find the missing side, Pythagorean theorem. 9 minus 1 is 8. The square root of 8 simplifies to 2 square root of 2. It's positive because we're in quadrant 1. So now, inverse sine of 1/3 generates a theta reference right triangle. There it is. Using that theta as your reference angle to find cosine, that would be adjacent to square root of 2 over 3. There's my answer. Sine of inverse tangent of 7. 7's positive. We're in quadrant 1. So again, build a quadrant 1 right triangle. Excuse me. Opposite over adjacent, 7 over 1. Pythagorean theorem is going to give us 50 for r squared. Take the square root. Simplified 5 square root of 2. That's my hypotenuse. So again, that's my theta. Then sine of theta. All right, opposite, 7 over 5 radical 2. but then we got to rationalize the denominator, multiply the top and bottom by the square root of 2, you get 7 square root of 2 over 10. Finding the inverse values using a calculator. So again, what we can do is say, take the secant of both sides, secant of y equals 4, and if you have to, write the inverse of secant y, which is 1 over cosine y, and as soon as you do that, we want to put 4 over 1 because we build that proportion. You flip both of them, and now you do the inverse cosine of 1/4. So notice the pattern here. If it's inverse secant, then it's going to be its reciprocal inverse cosine, but you also take the reciprocal of the argument. Two reciprocals going on. Go to the calculator, type it in, make sure you're in the degree mode. For degrees, that comes out to be 75.52 degrees. Switch it over to the radian mode. I get 1.318 radians. All right, so if we try the shortcut here, arc cotangent is like saying inverse cotangent. Its reciprocal is tangent. Inverse tangent of, then take the reciprocal of this decimal, 1 over negative 0.3541. So let's see if that works. I go through my steps. Take the cotangent of both sides. Flip this to 1 over tangent theta. There's this decimal over 1. Flip it. Okay, there's my reciprocal of my fraction. Then I take the inverse tangent of both sides. Now I'm ready for the calculator. Inverse tangent, again, negative argument is going to give us negative degrees. And then switch it to radians. You should also get negative radians.